I'm going to be talking about transient heat's characterization of sword cross-sections during quenching. Now, the forging process of Japanese swords have been around for centuries and involves making high and low carbon mahogany steel, high carbon steel for the edge, low carbon steel for the core, and when the final shape is obtained, it is placed in a furnace and then quenched. Now, the geometry we're using is diamond-like, where the dimensions are H1, H2, H3, and then W. And the convection coefficient away from the sword is determined from this chart, where the edge uses little h1 and the remainder uses h2, and this is due to the thickness of insulating clay. Now, the parameters used in the study are a constant strain triangle meshed using Delaney triangularization with 228 elements, 128 nodes, and a gamma 3 boundary condition, where an average temperature is used for the convection coefficients, where the average temperature is based on initial and final temperature of 383.7.5 degrees Celsius, where these are convection coefficients for the edge and the remainder. And we also use steel for the cross-section material. Now, time integration is done by using a Crank-Nicholson scheme with 0.01 seconds for our delta T, 12 seconds for our max, an initial temperature of 750 degrees Celsius, and a surrounding T infinity of 25 degrees Celsius. Now, our sword cools and arrives at 25 degrees Celsius. Our case is looked at is varying the height, the width, and the convection coefficient. Now, by changing the height of H3, and 2, you can see there's a much less rapid convection away from the sword as when we reduce the width. Now, this means that the thinner blade is going to have a much less quenching time, and so we'll want to pull that out of the bath much more rapidly than in the case of just changing the height. Now, if the sword forger had a bad day and decided to use more insulation on one edge, you can see that there develops a very asymmetric temperature distribution in the sword cross-section. Now, although the temperature distribution does seem to be relatively uniform, you can see this asymmetry developed, which will impact the sword properties. And so, in summary, we applied a finite element method to the quenching process of a Japanese katana, varying the cross-section dimensions and convection coefficient, and found that the thinner cross-section produced faster heat transfer to the steady state, while an asymmetric heat transfer coefficient shows asymmetric temperature distribution. Thank you very much.